This is Magic 063 Differentiable Manifolds. I'm Camille Mackenzie, and this is the podcast about tangent bundles. So if you think back to a picture that we had of tangent vectors in the plane a while ago, a tangent vector in the plane is a bound vector. It's bound to a particular point, and it has direction and length. The point at which it's bound, I'll write little x vector, and for the actual direction and length vector, I'll write capital X. And that's the point of R2 cross R2. And if we want to take all of the tangent vectors at all the possible points, then that is indeed all of R2 cross R2, and that's the tangent bundle for R2. That's the natural concept, even if you've never heard of the word manifold. One can't really visualize R4, but it's fine to think that at each point of the plane, we've got another plane somehow sitting on top of it. That's a little bit crooked, I'm sorry. These are meant to be axes that are parallel to the given axes. So there's a plane at each point consisting of all the tangent vectors. And that's quite a good mental picture to have. Now, think of the reals. In a way, this is more difficult. There's the real line. And a tangent space that sits on top of that would be virtually indistinguishable. So what's generally done is to think of the tangent spaces as perpendicular lines like this. So at that particular point, which might be 3/4, say, this vertical line through there represents the tangent space at the point 3/4. As a manifold, that's completely fine. That's the tangent bundle to the reals is the reals cross the reals again, and that's R2. So as a manifold, that's a completely valid picture. But as a geometric picture, it's not too good, because after all, the tangents to the real line are actually lying along the line. Same comment with S1. Think of the unit circle in the plane, and you very often see a picture of the tangent bundle of S1 as the infinite cylinder, on the basis that that's S1 cross the reals. And indeed that is, as a manifold, that is indeed the tangent bundle to S1. But again, the picture is misleading, since a genuine tangent vector to the circle would be lying in the same plane as the circle, something like that. There's actually something to prove here. It's not very difficult. We'll come back to it. But it's S1 is a very good submanifold of the plane. In fact, it's a zero set. And so we can get the tangent bundle to it quite quickly. But there is actually something to do. S2, this is a different kind of example. I'm changing colour here because I haven't got much room, but S2, of course, is the familiar sphere in R3, so the unit sphere centre of the origin. And we visualise the tangent spaces as being tangent planes, and of course they will almost always intersect. If you've got antipodal points, they'll be parallel, but any other pair of points, the tangent planes will intersect, and that's completely wrong as far as having a mental image of the tangent bundle is concerned. So TS2 is four-dimensional, and that's already a problem, but you've got the additional problem that you have to somehow mentally separate these various tangent planes from each other, and that's not a particularly easy thing to do. Further, one new thing, and again I'm going up the page, but I'm in black, TS2 is not a product manifold, we saw that TS1 is S1 cross R1. TS2 is not diffeomorphic to S2 cross R2. So that's a further complication, but that makes it interesting, and we'll come back to do this in more detail a little later. What's more, S3, the tangent space to S3, the tangent bundle, I mean to say, in S3 is S3 cross R3. And you may already know that if you've been doing the course on Lie groups and Lie algebras, or maybe from some other course. But we'll go through it with bare hands in a live session. And that's a worthwhile example to have for many different reasons. So now let's look at the actual manifold structure. First of all, an arbitrary manifold M. I'm going to say that Tm is simply the union of all the tangent spaces. In fact, I've got that written down here. Quite a lot of people will say that you ought to attach the point M to the tangent space and take that union. So that's a disjoint union, and that's completely fine. That makes absolutely explicit that M is actually a submanifold of M. Back in this picture here, I'd say that the zero in a particular tangent space is an element of the tangent space. But we can also identify it with the point little m of M. And in that way, I'd say that enables us to view M as a submanifold of Tm. Anyway, I'll work with this picture here most of the time, but if I ever need to emphasize things, then I'll come down to this picture down at the bottom of the slide. Okay. After all, when you look at the definition of a tangent vector, say at a point M0, the equation, or the derivation equation that it has to satisfy, involves the point M0. So the point M0 is actually firmly associated with the tangent vector x. So that's one reason why I'm happy with this simpler formulation here that I'm underlining rather heavily. Or, equally, if you do it in terms of derivatives of curves, then, I don't need the dot, then again, the point at which you're taking the derivative is explicitly associated with the tangent vector. The only other thing on this slide is TOR, the symbol for the projection map that takes the tangent vector and sends it to the point of M at which it lives, the point of the tangent vector to which it is tangent. And that's called the bundle projection. We'll come back to this terminology in a short while. There's quite a lot of different notations for this. P is quite often used, sometimes pi, but I'll stick with TOR. Okay, now let's do the actual manifold structure. So I'm going to start with a single chart for my manifold. Phi from an open set U in M to an open set phi of U in Rn. And I'll use this to obtain a chart for Tu of M, which is the union of all the tangent spaces at points of U. So TOR inverse of U, or simply the union over M in U of the tangent spaces at M. Now the image of the chart is going to be phi u cross Rn. And of course phi u is an open subset of Rn, so if we were going to talk about the tangent bundle to that, then indeed this is what we get. We get phi u cross Rn. We'll come back and talk about open submanifolds later on, but I think it's pretty straightforward to believe that as far as tangent vectors are concerned, if you're working in an open submanifold, it's the same as working in the manifold itself. So, as I said a moment ago, phi u is an open subset of Rn, so where are we? So phi u cross Rn is an open subset of R2n. Now, back to the chart phi. Every chart induces a system of local coordinates, and those local coordinates induce a system of tangent vectors at the points of the chart. So these are the things denoted partial I, and we put an alpha on them if we need to talk about phi alpha. These are the tangent vectors to the coordinate curves in U, and they're defined in this way. We take, operating on a function f, we transfer f over to the open subset phi u of Rn and differentiate in the ordinary way along the ith coordinate line. Okay, and that defines partial I at the point M. Now I'll use that to define phi tilde from Tu of M to phi u cross Rn. Namely, any tangent vector to a point little m will be a finite linear combination of these basis vectors, partial I, and real coefficients capital X of I. And I simply map that across to M and the n coordinates of the tangent vector. And it's clear, isn't it, that that's a bijection, and we've got to look at the overlap maps. We'll do that next. So I want to look at the overlap maps. I take two charts, phi alpha and phi beta for M, and I'm assuming that they overlap, so the intersection U alpha beta isn't the empty set. And I'm going to derive from them the two charts for the tangent bundle, phi tilde U alpha and phi tilde beta. Okay, and I want to calculate the overlap map for that. Now this is something that's best checked by yourself, but there are two components after all. There's the open set phi alpha of U alpha beta going across to phi beta of U alpha beta, and of course that is simply the overlap map on the manifold. On the other hand, for the components of the tangent vectors, that's the capital X tilde, this goes across to the effect of applying the derivative matrix of the overlap diffeomorphism at the point little x that we're concerned with to capital X, the coordinates of the tangent vector. And this is a good thing to check for yourself. We can think of this briefly like this. It's a bit rough. It's not, strictly speaking, completely accurate. But the first component is certainly the local diffeomorphism, the diffeomorphism overlap for the charts on M, and then the derivative matrix for them. So that's the manifold structure. It is actually very routine. You could put it in a few words by saying you take the overlap diffeomorphisms for the manifold and you apply the derivative matrix or Jacobian matrix to that. Or, if you think a little bit more sophisticatedly, you apply the tangent functor to it, and that gives you the charts for the tangent bundle. And there's very little to it, but then the tangent bundle is actually a very easy thing to work with. The problem is with visualizing it. And the slightly misleading diagrams that you tend to work with in 2 or 3 dimensions. But the actual object itself as an abstract manifold is actually quite a straightforward thing to use. So I want to run through the examples again. The tangent bundle to Rn is Rn cross Rn, and of course we built that in right at the start by saying that our charts would take values in open subsets of Rn cross Rn. The first component is the base point, and the second component is the actual tangent vector. The bundle projection is Tor, and it maps onto the first component. And in general, of course, the second component changes depending on which coordinate system you're in. Tangent bundle to S1 is S1 cross R. The bundle projection is again just projection onto the first factor. The tangent bundle to S2 is not the product manifold, and we'll come back to this example in a little while. But it's still the case that every tangent vector to S2 is associated with a particular point of S2, and that gives us the Tor map. And lastly, the tangent bundle of S3 actually is diffeomorphic to S3 cross R3. And as I said, we'll do that in detail. So that's it for now. We will come back and talk about the tangent bundle as a geometric entity in its own right later on. But just for now, its importance is that it's the basic object for everything to do with differentiation. And it's the start of the apparatus of differentiating objects on manifolds. Okay, that's it for now.